All right, today we're going to pull back the curtain on something you've probably never even thought about. It's this incredible, totally invisible system that makes sure your favorite refrigerated dessert is not just delicious, but also perfectly safe. And it all starts with a simple snack.
I mean, really think about it. We're not talking about whipping up a small batch in your kitchen. No, we're talking about industrial-scale production. Millions and millions of these little cups have to be made, cooled down, and kept fresh. How in the world does a factory even begin to manage that kind of volume?
Okay, so here's the thing. The secret to making pudding on this massive scale isn't just a bigger kitchen. It's a huge, incredibly powerful cooling system. And the chemical that fuels this whole thing, well, it's so good at its job, but also so potentially dangerous that it needs this unbelievably detailed safety plan just to keep everything running smoothly.
So what's the big secret? It's all about the cold. You gotta go from a warm, freshly cooked product to a perfectly chilled dessert that's ready for the supermarket aisle. To do that, you need industrial-strength cooling, and it has to be absolutely 100% reliable.
You see, the fridge in your kitchen just isn't going to cut it here, not even close. To cool down enormous vats of pudding, plus entire storage rooms and all the processing equipment, these factories rely on a closed-loop system. It's constantly sucking heat out of the building and moving it outside. And to do that, you need a special kind of chemical workhorse.
And here it is. Meet anhydrous ammonia. That name basically just means ammonia without water. And let me tell you, this stuff is unbelievably good at its job, absorbing heat. That incredible efficiency is exactly why it's the go-to refrigerant for huge food plants, just like the Cozy Shack facility we're looking at. But it's got a pretty serious dark side.
And this, right here, is the central conflict of our story. Ammonia is the hero that makes all of this mass production possible. But at the same time, it's a major hazard that has to be respected and controlled with some serious precision.
I mean, the contrast here is pretty stark, right? On one hand, you've got the hero. Ammonia is just fantastic at absorbing heat. It's the engine of the entire cooling process. But on the other hand, it's a serious hazard. It's toxic if you breathe it in, it's corrosive to your skin and lungs, and the whole system keeps it stored under immense pressure. If one thing fails, it could be catastrophic.
And to really put that danger into perspective, look at this number, 300 parts per million. That's the official IDLA level, which stands for immediately dangerous to life or health. At that concentration, which is a tiny, tiny amount, the air is so toxic it's an immediate threat. So, the million-dollar question is, how on earth do you manage a chemical this powerful? Well, you do it with a plan, a massive, comprehensive, and just meticulously detailed blueprint for safety that has to account for every single pipe, every valve, and every possible thing that could go wrong. So let's take a look at the rulebook. This is the Process Safety Information, or PSI. And believe me, this isn't just a stack of boring paperwork, this is the master guide. It has everything anyone who works with this system could possibly need to know. The chemical hazards, the details of the equipment, the technology. It's really the foundation of the entire safety program.
And hey, don't just take my word for it. This quote comes directly from the facility's own safety document. It calls the PSI the foundation for everything that comes after, from just safe day-to-day operations to knowing exactly what to do in an emergency. It all starts right here.
Now, a really critical part of that PSI is this thing, the P&ID. That's the Piping and Instrumentation Diagram. The best way to think about it is as the ultimate map of the whole system. It shows every single component, the compressors, the evaporators, the vessels, and every little valve that connects them. For the engineers and operators, this map is absolutely crucial. It's how they understand how this whole machine actually works.
So what's this whole system actually doing? Well, we can simplify it down to 4 basic steps. First, the liquid ammonia evaporates inside the building, and in doing so, it absorbs a ton of heat and chills the pudding. Then compressors squeeze that gas, which makes it super hot and high pressure. Next, that hot gas moves outside, where big condensers release all that heat into the air, turning the ammonia back into a liquid. And finally, that liquid is sent right back to the start to begin the cycle all over again.
Okay, so we've got this powerful chemical, and it's moving through this really complex system. How is that danger actually controlled? Well, it's not just one single thing. It's multiple layers of protection, starting with the machinery itself. Let's see how these layers build on top of each other.
The first layer is what we call engineering controls. These are the built-in automated safety features. So you've got ammonia detectors that will sound an alarm at just 25 parts per million. Remember, the danger level is 300, so that gives everybody the maximum possible warning time. You've got emergency ventilation systems, pressure relief valves to prevent pipes from rupturing, and of course, big red emergency stop switches to shut the whole thing down in an instant.
The next layer is administrative controls. This is all about the people and the procedures. Everyone has to follow standard operating procedures, or SOPs, for every single task. There's required annual safety training, clear warning signs posted everywhere, and even special permit systems for any kind of high-risk maintenance job. This layer is all about making sure human behavior is as safe and predictable as possible.
And that brings us to the final layer of defense, personal protective equipment, or PPE. This is the gear that protects the individual person. For just routine tasks, it might be safety glasses and gloves. But for higher-risk jobs, that escalates to full face shields. And if there's a real emergency, we're talking full-on SCBA breathing gear and chemical suits, the whole shebang.
But here's the thing. All the technology and all the rules in the world, they're not enough on their own. The single most important safety system is a well-trained, well-prepared team of people all working together. This is the human safety net.
You see, safety is a shared responsibility. You have a process safety manager whose job is to oversee the entire program. But just as important is every single employee on the floor. They're responsible for following the rules and, maybe most crucially, for reporting anything at all that looks unsafe.
And here is just a perfect, simple example of that human element in action, the buddy system. For any task that's considered high risk, nobody works alone, ever. Two qualified people work together. It's such a simple, low-tech solution, but it provides an immediate, powerful safety net. It's really all about having each other's backs. So, let's zoom back out. What does all of this really mean? It means that every single time you open a refrigerator door at the grocery store, you are interacting with the end result of countless invisible systems, all designed to protect workers, the public, and you.
Right. That cup of pudding didn't just magically appear. It is the product of a massive, hidden machine. A machine that's not just made of steel pipes and compressors, but of detailed diagrams, strict procedures, and a culture of safety that's shared by every single person involved.
And that really brings us to our final thought. From the traffic lights that manage our daily commutes to the water treatment plants that purify what we drink, our world is absolutely filled with these complex, invisible safety systems. So the real question is, what other ones are hiding in plain sight, quietly keeping your world running day in and day out?